Hi, everyone. If you'd like to hear the reading on what is heat, just listen up. It's time for your annual physical. The doctor comes in and begins her exam by placing a metal stethoscope on your back. You jump a little and say, "Whoa, that's cold." What is it about the stethoscope that makes it feel cold? The answer has to do with how energy moves between the metal and your skin. In this section, you'll learn about this kind of energy transfer. Transferred thermal energy. You might think of the word heat as having to do with things that feel hot, but heat also has to do with things that feel cold, such as the stethoscope. In fact, heat is what causes objects to feel hot or cold, or to get hot or cold under the right conditions. You probably use the word heat every day to mean different things. However, in this chapter, you will use only one specific meaning for heat. Heat is the energy transferred between objects that are at different temperatures. Why do some things feel hot while others feel cold? When two objects at different temperatures come into contact, energy is always transferred from the object that has the higher temperature to the object that has the lower temperature. Look at Figure 1. The doctor's stethoscope touches your back. Energy is transferred from your back to the stethoscope because your back has a higher temperature, about 37 degrees Celsius, than the stethoscope, probably room temperature about 20 degrees Celsius, has. This energy is transferred quickly, so the stethoscope feels cold to you. Heat and thermal energy. If heat is transferred energy, what form of energy is being transferred? The answer is thermal energy. Thermal energy is the total kinetic energy of the particles that make up a substance. Thermal energy, which is measured in joules, depends partly on temperature. Something at a high temperature has more thermal energy than it would have at a lower temperature. Thermal energy also depends on how much of a substance there is. Look at Figure 2. The more particles there are in a substance at a given temperature, the greater the thermal energy of the substance is. Reaching the same temperature. Look at Figure 3. When objects that have different temperatures come into contact, energy will always be transferred. Energy will pass from the warmer object to the cooler object until both have the same temperature. When objects that are touching each other have the same temperature, there is no net change in the thermal energy of either one. Although one object may have more thermal energy than the other object, both objects will be at the same temperature. Conduction, convection, and radiation. You already know several examples of energy transfer. You know that stoves transfer energy to soup in a pot. You adjust the temperature of your bath water by adding cold or hot water to the tub. And the sun warms your skin. In the next few pages, you'll learn about 3 ways to transfer thermal energy: conduction, convection, and radiation. Conduction. Imagine that you have put a cold metal spoon in a bowl of hot soup, as shown in Figure 4. Soon the handle of the spoon warms up, even though it is not in the soup. The entire spoon gets warm because of conduction. Thermal conduction is the transfer of thermal energy from one substance to another through direct contact. Conduction can also occur within a substance such as the spoon in Figure 4. How does conduction work? When objects touch each other, their particles collide. Thermal energy is transferred from the higher temperature substance to the lower temperature substance. Remember that particles of substances at different temperatures have different average kinetic energies. So when particles collide, particles with higher kinetic energy transfer energy to those with lower kinetic energy. This transfer makes some particles slow down and other particles speed up until all particles have the same average kinetic energy. As a result, the substances have the same temperature. Conductors and insulators. Substances that conduct thermal energy very well are called thermal conductors. For example, the metal in a doctor's stethoscope is a conductor. Energy is transferred rapidly from your warm skin to the cool stethoscope. That's why the stethoscope feels cold. Substances that do not conduct thermal energy very well are called thermal insulators. For example, a doctor's wooden tongue depressor is an insulator. It is at the same temperature as the stethoscope, but the tongue depressor doesn't feel cold. The reason is that thermal energy is transferred very slowly from your tongue to the wood. Some typical conductors and insulators are shown in Table 1 at the right. Convection. A second way thermal energy is transferred is convection, the transfer of thermal energy by the movement of a liquid or a gas. Look at Figure 5. When you boil the water in a pot, the water moves in roughly circular patterns because of convection. The water at the bottom of a pot on a stove burner gets hot because it is touching the pot, conduction. As it heats, the water becomes less dense because its higher energy particles spread apart. The warmer water rises through the denser, cooler water above it. At the surface, the warm water begins to cool. The particles move closer together, making the water denser. The cooler water then sinks back to the bottom. It is heated again, and the cycle begins again. This circular motion of liquids or gases due to density differences that result from temperature differences is called a convection current. Radiation. A third way the thermal energy is transferred is radiation, the transfer of energy by electromagnetic waves such as visible light and infrared waves. Unlike conduction and convection, radiation can involve either an energy transfer between particles of matter or an energy transfer across empty space. All objects, including the heater in Figure 6, radiate electromagnetic waves. The sun emits visible light, which you can see, and waves of other frequencies such as infrared and ultraviolet waves, which you cannot see. When your body absorbs infrared waves, you feel warmer. Radiation and the greenhouse effect. Earth's atmosphere acts like the windows of a greenhouse. It allows the sun's visible light to pass through it. A greenhouse also traps heat energy, keeping the inside warm. The atmosphere traps some energy too. This process, called the greenhouse effect, is illustrated in Figure 7. If our atmosphere did not trap the sun's energy in this way, most of the sun's energy that reached Earth would be radiated immediately back into space. Earth would be a cold, lifeless planet. The atmosphere traps the sun's energy because of the greenhouse gases such as water vapor, carbon dioxide, and methane, which trap energy especially well. Some scientists are concerned that high levels of greenhouse gases in the atmosphere may trap too much energy and make Earth too warm. Heat and temperature change. Have you ever fastened your seatbelt on a hot summer day? If so, you may have noticed that the metal buckle felt hotter than the cloth belt did. Why? Thermal conductivity. Different substances have different thermal conductivities. Thermal conductivity is the rate at which a substance conducts thermal energy. The metal buckle of a seatbelt, such as the one shown in Figure 8, has a higher thermal conductivity than the cloth belt has. Because of its higher thermal conductivity, the metal transfers energy more rapidly to your hand when you touch it than the cloth does. So, even if the cloth and metal are at the same temperature, the metal feels hotter. Specific heat. Another difference between the metal and the cloth is how easily each changes temperature when it absorbs or loses energy. When equal amounts of energy are transferred to or from equal masses of different substances, the change in temperature for each substance will differ. Specific heat is the amount of energy needed to change the temperature of 1 kilogram of a substance by 1 degree Celsius. Look at Table 2. The specific heat of the cloth of a seatbelt is more than twice that of the metal buckle. So for equal masses of metal and cloth, the same thermal energy will increase the temperature of the metal twice as much as the cloth. The higher the specific heat of something is, the more energy it takes to increase its temperature. Table 2 shows that most metals have very low specific heats. On the other hand, the specific heat of water is very high. This is why swimming pool water usually feels cool even on a hot day. The same energy heats up the air more than it heats up the water. Heat, temperature, and amount. Unlike temperature, energy is transferred between objects that cannot be measured directly. Instead, it must be calculated. When calculating energy transferred between objects, you can use the definition of heat as the amount of energy that is transferred between two objects that are at different temperatures. Heat can then be expressed in joules. How much energy is needed to heat a cup of water to make tea? To answer this question, you have to consider the water's mass, its change in temperature, and its specific heat. These are all listed in Figure 9. In general, if you know an object's mass, its change in temperature, and its specific heat, you can use the equation below to calculate heat. Calculating heat. Using the equation above, you can calculate the heat transferred to the water. Because the water's temperature increases, the value of heat is positive. You can also use this equation to calculate the heat transferred from an object when it cools down. The value for heat would then be negative because the temperature decreases.